Welcome to the Deep Dive. We're here to unpack insights from really vital research, giving you the knowledge you need fast. Today, we're tackling something fundamental: water, specifically drinking water. With climate change, increasing drought, especially in arid places, those rivers we counted on, many are becoming seasonal, and that makes groundwater absolutely critical. But here's the kicker: it's not just any groundwater. We need high-quality drinking water. Standards like, say, the WHO's, they set limits for contaminants, sure, but they don't always tell you the whole story about quality within those limits. And trying to figure that out by looking at, maybe dozens of different factors, it gets really complex, fast, without the right kind of system. So, what if there was a smarter way? That's what we're exploring today. A powerful new strategy that combines data mining, digging through data, with geographic information systems, GIS, to zero in on these high-quality zones. Our mission in this deep dive, to show you exactly how this combined approach works, what tools it uses, and what it actually found about groundwater in a real place. This all comes from a really interesting research paper called Decision Tree-Based Data Mining and Rule Induction for Identifying High-Quality Groundwater Zones to Water Supply Management. Okay, let's unpack this a bit. We know water's essential, obviously, but what's the really specific, urgent issue this research is getting at, especially in those drier regions you mentioned? The stakes sound, well, pretty high.
They really are. What's critical, you see, is how these global changes are really amplifying the problem. More drought years mean less reliable rivers. So groundwater stops being just an alternative. For many communities, it's becoming the only reliable source for drinking water. Then the challenge shifts, doesn't it? It's not just about finding water anymore, but about making sure it's safe, it's high quality. Historically, studies might map one thing, like salinity or maybe pH. But putting all those maps together effectively, that was always the hard part, getting that single, clear picture. Which brings up a key question. How do you pull all that complex, varied information together efficiently? You need something robust for making good decisions.
Yeah, and that's exactly where things like decision support systems, DSS, and geographic information systems, GIS, come into play. They're incredibly valuable here. Think of a DSS as like a smart assistant for the people making the calls, right? It helps analyze tons of data. And GIS is crucial when that data is spatial, when it matters where things are. It lets you visualize it all on a map.
Makes it much easier to see, okay, here's the good water, here's the not so good.
Right, maps you can actually use. So this paper talks about a novel hybrid use of data mining and GIS. That sounds like the really interesting part. Can you walk us through what that actually means for finding this high-quality groundwater? How is it different?
Absolutely. So data mining is essentially about finding hidden patterns in big piles of data. It's part of this broader thing called knowledge discovery in databases, or KDD. Imagine like sifting through mountains of information to find these little nuggets of insight, these rules hidden in the numbers. The core tool they used here, decision tree algorithms. These are really powerful for classification. Think of it like a flowchart or maybe a game of 20 questions. It asks a series of yes or no questions about the data to sort of systematically narrow things down until it can classify the water sample. Is it optimum quality, medium, poor? And the real beauty is these algorithms can turn those complex relationships they find into simple, easy to understand if-then rules.
Oh, okay. Like if the conductivity is below this level and the pH is in this range, then the quality is likely optimum, that sort of thing.
Exactly. Precisely like that. Makes it very practical. And the study didn't just use one type. They actually tested 5 different decision tree algorithms to see which one worked best for this specific task. Things like ordinary decision tree, random forest, random tree, and a couple of others, ID3 and Shimidi.
Okay, so the real innovation here seems to be taking that raw field data, using these clever algorithms to extract those clear if-then rules, and then using GIS to put it all on a map. A map that, water managers or local authorities, even people without a deep data science background, can look at and understand. It makes complex science usable.
That's the goal. Make it actionable.
So the study aimed to, first, figure out which water quality factors mattered most. Second, see how well these different algorithms actually performed. And third, create these practical groundwater quality maps for a specific area.
Correct. Those were the prime objectives.
So where did they actually do this? Where did they apply this cutting-edge method? Tell us about the study area and how they got their hands on the necessary data. It's always good to ground these things.
Right. They focused on Tabriz City and its surrounding township, which is in northwestern Iran. It's a semi-arid area. About 1.5 million people live there. And like many places, they're facing water supply pressures because of recent droughts. Most of their water comes from dams, but they also rely on some wells. For the data, the researchers measured 8 different groundwater quality parameters, things like uh, sulfate, hardness, total anions, pH, calcium, magnesium, chloride, and also electrical conductivity, or EC. They got these measurements from 80 different observation wells spread across the area. And then this is crucial. They had water quality experts come in and actually rank the quality of the water from each of those wells, from Class A, meaning optimum, all the way down to Class I, poor quality.
Okay. 80 wells, 8 parameters. That still sounds like quite a bit to work with. You mentioned earlier finding the nuggets. How did they narrow down those 8 parameters to the ones that were, well, most important? That sounds like feature selection.
Exactly. Feature selection. It's a really vital step. You don't want to throw everything into the model if some factors aren't actually telling you much.
Yeah.
Or if they're redundant. It just adds noise. So in this study, they used the random forest algorithm again. Actually, it's quite good at this as part of that KDD process to pinpoint the most effective parameters. And it turned out of the original 8, only 4 really stood out as the key drivers for predicting that expert-ranked quality.
And those were?
Electrical conductivity, EC, pH, hardness, and chloride. Those 4 became the inputs for the next stage, the rule induction part.
Got it. EC, pH, hardness, chloride. Now, here's a really interesting methodological point they explored. Comparing performance using continuous versus discrete data. Can you first just quickly clarify that difference again and then tell us what they found? Which worked better?
Sure. So continuous data is just the raw measurement. Like the pH reading is exactly 7.3, or the EC is 11/2050 octan C-meter. It's the precise number. Discrete data is when you group those numbers into categories. So instead of 1150, you might just classify that EC level as medium quality based on some predefined ranges. Like maybe anything under 1,000 is optimum, 1,000 to 2,000 is medium, and over 2,000 is poor. You lose some precision, but you gain simplicity.
Right, simplifying it into buckets. So what happened when they compared the algorithms using these 2 types of data?
Well, the finding was pretty clear-cut. The rule induction, using the continuous data set, the raw numbers, showed significantly better performance, higher accuracy, better capability overall.
Interesting. So keeping the detail mattered.
It really did, for these algorithms at least. And when they looked at the specific algorithms using that continuous data, random forest, or RF, was the definite winner. It achieved an impressive 97.10% accuracy. Really quite high.
Oh, 97%.
Yeah. The ordinary decision tree, ODT, also did very well. Came in second with 91.30% accuracy. And random tree RT was acceptable too, around 79.71%.
And what about the discrete data? Did any algorithms work well there?
Well, that's where it gets less impressive. Even algorithms like ID3 and CHADE, which are often considered good for nominal or categorical data, like the optimum, medium, poor labels, their performance was described as very poor in comparison. ID3 actually had the highest accuracy among those tested on discrete data, but it was only 71.43%, with a kappa coefficient suggesting only moderate agreement. So a huge difference.
Okay, so the takeaway there is, for this kind of groundwater quality modeling with these specific decision trees, using the continuous numerical data seems to be the way to go. And random forest was the star performer.
Precisely. That was the key finding.
So, armed with that knowledge and using the rules derived from the best algorithms, RF, ODT, and RT on the continuous data, what did the final groundwater quality maps for Tabriz actually show? What's the practical outcome for that region?
Right. So they took those IFTHED rules generated by RF, ODT, and RT.
Yeah.
Then using GIS, specifically a technique called ordinary kriging, to estimate values between the well locations. They created spatial distribution maps for those 4 key parameters: EC, pH, hardness, and chloride. They did some checks first, like Moran's eye for spatial patterns, and some data transformations to make sure the statistics worked out properly.
Okay, standard geospatial stuff. And then they combined these layers using the rules.
Exactly. The rules told them how to combine the different parameter maps to predict the overall quality class across the entire area. And the resulting maps, they confirmed a really clear spatial trend, a vital piece of information. Groundwater quality generally decreases as you move from the south towards the north, and also as you go from east to west across the Tabriz area.
A distinct gradient then, south and east being better.
Yes. The southern parts, which get recharged by water coming from the nearby Sahan Mountains, consistently show the bit quality optimal for drinking. But in contrast, the northwestern and western parts of the city and township, generally poor quality water, unfortunately.
That's incredibly useful information for planning, isn't it? Where to site new wells, where to protect resources.
Absolutely.
Yeah.
And because the random forest algorithm had the highest accuracy, the map generated using its rules was considered the most reliable one. That RF map showed quite clearly Only the southern and southeastern areas really had that optimum quality water. There was sort of a thin band of medium quality around it.
And the rest.
The rest was largely classified as poor or near poor for drinking purposes. It gives a very specific spatial picture of where the high-quality resource is concentrated.
So wrapping this up, this deep dive has really shown how this integrated approach, combining data mining's pattern finding with GIS's mapping power, can be incredibly effective. It successfully classified water quality and pinpointed those crucial high-quality zones, even using a relatively manative data set from those 80 wells.
Yeah, and the real benefit, I think, is how practical it makes things. It takes complex expert knowledge and environmental data and translates it into these clear if-then rules using those decision tree methods. Rules that, as you said, non-experts can then easily pick up and use for making really critical decisions about water supply management. That bridge is so important. And based on this study, for numerical data like water quality measurements, random forest, and ordinary decision tree, really seem like strong recommendations for getting accurate results.
It really makes you think. Imagine applying this kind of data-driven insight elsewhere. Not just for water, but, for other critical resource challenges. Think about figuring out the best agricultural land, or planning urban development more sustainably, or maybe even tracking environmental health indicators. What other big, complex societal or environmental issues could we tackle better if we could distill the data down into these kinds of actionable if-then rules? Rules that empower decision makers, not just scientists. That's definitely something worth pondering.